So
okay.
we'll go directly to the next speaker, who is
Okay.
Dr. Cengiz Toklu.
Okay.
We have had a fair bit of. We know each other from quite a while back, and he was quite involved in my previous project, well, Moon Mine. Professor Toklu has been directing and supervised numerous projects in Turkey and been teaching in several universities, mainly in Turkey as well. Interestingly for me, probably for nobody else here, he has also been working with finite element methods, and in particular with optimization. Cengiz, are you there? Right.
Start my video, yes, and share screen.
And the floor is yours, and the air
Yeah.
and ether. And that's a good screen. I think you need PowerPoint as well.
Okay, thank you very much. I think you are seeing the screen.
We are seeing the screen, but it's the browser.
Yeah, we're just seeing the files. We're not seeing the presentation yet. There we go.
Presentation, good.
Yep.
Thanks.
There we go. Okay. Okay, thank you very much. Now, we had very good presentations until now. I hope this will be, informative also in some ways. So we will talk about lunar regolith simulants that we have produced here in Turkey, and they're using lunar construction. And also we will talk about a few generalities. So the presentation will be in three parts. One of the first part will be production of lunar soil simulants. The second part will be about lunar construction materials. And lastly, I will have a few words about generalizations. Now, most of the information given in this presentation is taken from these two recent publications. Now, there's about 400 kilograms of lunar soils and rocks on Earth, 380 kilograms brought through Apollo missions, about 300 grams brought through Luna missions during Soviet times, about 1.7 kilogram brought recently by China, and also some lunar rocks ejected from Moon after the meteor impacts. They are, of course, so precious and not of big amount. So if we want to make research on lunar soil, we have to produce resembling materials there. Now, of course, this study, which is on lunar soils, can be affected on Mars soil also. Now, these are the famous, Apollo missions from Apollo 11 to Apollo 17, and the samples returned through that missions. You see that from the first one was 22 kilograms, the last one was 110 kilograms. So these are the positions of Apollo missions on the Moon. Now, this table is taken from this publication, which is on the top, blue color. So we have Apollo missions on the left, and the components of oxides, which are measured on these samples. There are 18 rows here. Some of them are averages. Some of them are, given numbers, which are, the soils which are really broad. but some others are averages. So I have here 18 samples in this table. Now, not all these soils are of the same characteristics. As you can see here, at the x-axis, we have the oxides, and on the vertical axis, we have the percentages of components. You'll see that, that there are big differences from soils from point to another point, which is the same as on the world. So this is, if we separate mare areas, highlands, and mixed areas, so we have such distributions. Now, this production of lunar soils is an international project. There are many countries and many universities or many other institutions working on this project. And of course, working on such a project, as to our experience, is not very expensive and can be carried on with many countries. And of course, they have the effect of improving the level of science and technology of those countries. Here we have a list of lunar soil simulants, which are, produced until now, until very recently. You see that there are many countries here, and many different types of soils produced. This table is also taken from that publication. The countries which have produced soil simulant until now were Australia, Canada, China, Germany and Italy in European Union, India, Japan, South Korea, USA, and lastly, we have done it in the last years. Now, these products are obtained usually by going to, volcanic places in the countries and taking soils from them and finding mixes so that they will be close to the soils brought from the moon. I have given here a few examples. For example, the product obtained in Marshall Space Center was obtained by adding minerals olivine and ilmenite to samples taken from a mine in Montana. In Australia, they have taken material from a mine. In Korea, they have taken basalt samples from a certain place. In Italy, material from Bolzano crater. For Japan, they have taken materials from many countries in the world. So we have also produced followed a simple, similar way. So from 9 volcanic areas in Turkey, this is the map of Turkiye, from 9 different volcanic areas, we have taken soils. So these are the 9 points, and to them, from mines and different organizations, we have obtained olivine, fly ash, Ankara, 2 types of basalt, and ilmenite. So we had in our hands 14 materials to investigate. So these are the chemical analysis of those samples. So you see that we have tried to find the same type of oxides in those materials. Now then, we had a table for the components, chemical composition of the lunar soils, and also we have a table for the materials taken which are in our hands. Then the problem is to make a combination of these elements to samples taken from different parts in Turkey, and make a combination such that, for example, the chemical composition will be close to this one, for example. What we have done is we have tried to make mixes which are similar to all of them. So to all 18 types of lunar soils, we have tried to make composite, we have tried to find mixes. Of course, this is done by an optimization process. And so the calculations, I will not go into details, but for example, the distance between our soil, our simulant, and the lunar soil, the distance is measured in such a way. And of course, we have used weight factors because some percentages were were very close to 60%. Some other percentages were very close to the 0%. So if we didn't use, weight factors, then the result would not be acceptable. So we have used weight factors, and then we have used Jaya algorithm. It is one of the optimization algorithms. Just, to make a point, the original way of this Jaya algorithm is given in the second line with absolute signs. We have shown later that these absolute signs should not be used. So we have used the first line here as the Jaya algorithm. Actually, in this problem, that is immaterial because the axis, the percentages taken from materials were all positive. So taking absolute value or not, it is not important. Now, this is the way that this optimization process approaches to the final result. So this is 3 independent runs for a given problem. Now, the result was like this. So we have seen that, the best result we have found were for a soil from Apollo 14, and the worst one was a soil from Apollo 16. That means that even we had, used 14 types of materials, the results were very different. So this is the distance measured. So for Apollo 14, the distance measured according to this equation was 10.00. For the last one, for the worst one, the distance was 20.14. Very different. You can here you can see the best and the worst results. Here, this is the best results corresponding to a Apollo 14 sample with distance 10, and this is the worst one, which is with a distance measure of 27.14. This is the one that we have given the name TBG1, and which we are using in our further studies. So you see that this is the soil that we have obtained. And so if you want to compare, for example, that one, here, looking to the last two lines, the last line is our simulant, and the one above it is the lunar soil. So you see that the distances are really small, 48, 40, 50, 2 to 17, 16, 0, 0, 10, 9, etc. So as you see in the graph, the simulant is very close to the original soil. Now, at the same year that we were looking for we were trying on this project, the Chinese mission also, CE5 has resulted, and they brought 1.7 kilograms of soil, and the characteristics of that soil also are published. And since we have the possibility of making, similar to any type of material, we also have tried this, and very quickly we have obtained this result. Now the blue one is the original one, red one is our simulant. you see that it is, the distance is 21. So what is important here, what I want to say here is that even using, 14 types of samples from the world, it was, you cannot find exactly a better delta for that. So now we are working on another project so that we will use more soils, more types of samples in order to approach better to the soils coming from other places from Moon or from Mars. Now, coming to the lunar construction materials, I am trying to be quick. Now, of course, Professor Benaroya will talk about these things in his speech. The materials that we are going to use in structures on Moon, we are in need of tension-resistant materials and tension-resistant structures. So the structures are most likely will be spherical and similar. So, and other types also. For example, this is a tensegrity structure, which are made by bringing from Earth very small types of materials, just struts and cables. And this is the artist view of spherical structures combined together with cylindrical tubes, etc. Now, the first material that we are going to use on Moon is regolith. But first of all, the excavation of regolith also is very difficult, because if on Earth we are using very heavy types of excavators, but we cannot bring them to the Moon because they are very heavy. We will bring to the Moon, excavators of weight, let us say a few hundred kilograms, and they will be effective on the Moon 1/6 of effectiveness that they will have on Earth. So that's a problem. So we have to find a problem to solve that. We have to find a solution to solve that problem. And for regolith, first of all, we will use them as they are, because we will not have any plant to elaborate them. We will use, for example, gabions. We will use sandbags, or perhaps we will make reinforced regolith, as I call them, and with the abbreviation RIRI. So these are the ways of using regolith in the first stages. So this is, for example, to see that what types of terrestrial materials and in-situ materials we are going to use on Moon. Of course, at the beginning, we will not use any lunar material. We will use only material brought from the Earth, and qualitatively, there will be such a diagram. And we will not forget that, bringing a material from Earth to Moon, the cost is 130,000 kilograms, dollars per kilogram. Of course, this cost will change by time, but this is the best estimation today. And of course, this is not the only disadvantage for bringing material from Earth to Moon. Ben has given some other disadvantages also. Now, this is to show that the materials that we are going to use there must be, we will need tension-resistant materials. For example, if you have a floor on Earth, 30 meters square, then by since it is only compression, we will need a column there with a small computation. 750 millimeters square of column will be sufficient. But if you make that structure the same on Earth, on the moon, with 2 meter thick regolith on it, for the protection. Then the total compression load will be 175 kilonewtons. Here it was on Earth it was 150 kilonewtons. On Moon it is 175 kilonewtons compression. But if there is a pressure of 1 atmosphere here, the tensile force is 3,000 kilonewtons. So that is not comparable with compressive load. So we will need on the structures on the moon, most of the time we have to be able to find tension resistant materials, and it is very difficult because all materials that we can obtain by using lunar regolith are more compression resistant than tensile resistant. Concrete, for example, is not a tensile resistant material. These are the results of the studies that are done until now for these types of concretes made by lunar soil. You see that on the first column we have compression resistance. On the right we have flexion strength in flexion. So normally, for example, if you look here in flexure, in bending, now the strength is 7 megapascal. In compression, it is 20 megapascal. So this is the general case. We will always have the problem of tensile resistant materials. So for a long time, we must bring tensile resistant materials from Earth. Now these are some procedure for obtaining solar break, etc. This is a solar break obtained in this manner. Now, I want to give a few words for lastly. Now, I think there is a spiral of world history, which is something like this. If we have a world, if we are in a region with some resources, with a given nature, that resources and nature gives us our economy and technology. Whenever it is possible, this economy and technology allows us to go to new lands, so that our world, gets bigger. Now that new world then has new resources and that new nature. So we then will have a stronger economy and stronger technology. Then we will be able to conquer, invade, or simply visit new areas. So this is what we have done until now in our history. And this is continuing. This is a natural phenomenon. We are now conquered. We know that we are living on a globe in 3 dimensions. But in for example, 2050, our world will be Earth and the moon and the space between them. And in 2100, it will be, world, Mars, moon, and the area between them. And that is something natural. That is a natural, continuation of the history of mankind. And man goes to everywhere he can go. This is an interesting, I find it very interesting, this simple graph. I have drawn it from minus 3000 history year to the 3000 year to show that around 2000, what we have done as humanity. Until now, all we have done going to the space is done just before 2000, and it is continuing. And so Gagarin is here, the moon is just before 2000, and Mars is coming, and Jupiter in in the year 3,000 perhaps. And so this is also, this affects me very much, you know, every time I see this email, I get excited. Now this is after Columbia. This was a, you know, Johnson Space Center exhibit manager. Please read it yourself, because I every time get excited when I read this thing. Thank you very much.
Thank you, Cengiz. Let's see, do we have any questions on this? I do have a question on the Regolith simulant, actually, and
Yes.
that is about magnetic properties.
Yeah.
From your picture, there is no, there's only one type of iron oxide, and I think Fe2O3 is the magnetic one, which apparently is not present in either the Lunar, the Apollo samples, or in your. Is that correct?
Yes. Yeah. I mean, these are the results, you know, given for Apollo samples.
Yeah.
And we have tried to follow that table. We have to fit our simulants to that table.
I guess my question is: have you checked if there is Fe2O3 in it?
No,
because that column wasn't in your chart, I think.
Which column?
The one with only dashes. These are samples, but in your, yeah. Well, yeah.
Sorry. This is the lunar samples, okay?
Yes.
And where are ours?
And do you also have 0? Because I know the Japanese simulant has a fair bit of Fe2O3, and that's the only one I have had contact with, actually. I don't think Fe2O3 was in your diagrams.
This is ours, yes.
Yes,
but
you have.
Yeah.
So my question is, have you actually checked for Fe2O3, or is FeO just a generic for iron oxide or rust?
Oh yeah, no, we didn't check for it. We did with this one.
Okay.
Okay.
Because the reason I ask is that I think it does have an impact on magnetic separation, if you want to use that to get iron.
I see. I see. Okay. Yeah.
So it could be worth, or just checking the magnetic properties if there is a reference on magnetic properties for the Apollo samples, which I'm not aware of.
Oh, yes, I will. You know, a few minutes ago, I have written to you, you know, in chat. I said that if you want, we are now working on producing new simulants. I hope that that project will have the result in a few months. And if you want, I will send to your center enough amount of lunar soil so that you can make your agriculture on that soils. And in that case, I will look to this fair problem also.
Yeah, good. Doing agriculture in lunar soil is one thing, but essentially it's the nutrients that is needed. So you then want to add at least nitrogen, because the plants need that. So but I'm also looking at mining properties and then the magnetic properties. It is one of the easier way to separate iron is to use a magnet, but that doesn't work well on FeO part, but it does work very well on Fe2O3 apparently.
Okay.
So thank you for that.
Any other questions? I'm excited. It's good to get more simulants out there.
Yep.
Especially, a lot of the older simulants, they're just not making them anymore. So there's not a whole lot of options if you wanted to buy them in bulk. Are you planning on actually selling them or having them available for researchers?
For researchers, I'm not, making something, commercial about it. I hope that, I will be able to send people whenever necessary, I'm trying to make it a university project. So not something commercial.
Right. But if somebody was like, hey, I really want to use your simulants in an experiment, they might be able to get their hands on some.
I hope so. Yes.
Okay, cool.
Okay.
Very good. So, Ben,
right.
should we go over to the message from the sponsor? Thank you, Cengiz.
Thanks, Cengiz. Appreciate it.
Thank
Good
you.
presentation.
Thank you very much.